Cool. So welcome. Today, we're super excited to present the topic 5 common code patterns that slow down your app. In this webinar, we'll explore prevalent challenges faced by app developers in delivering an exceptional mobile user experience. Examples we share today will be both applicable to iOS and Android. However, since we do have a special guest here today who is highly experienced in Android development, we will have a slight focus on Android. So first of all, we'd like to say hi. Today, we're thrilled to have Anastasia, who have 2 years of experience in solving different kind of performance challenges for different mobile apps. We also have Brian here, who is an Android development veteran of 13 years, also here to answer any questions you have for Android. And I'm Scarlett, your facilitator, who have been building product for mobile app developers, previously Fire advertising, now Fire performance enhancement to help you drive revenue.
Now, the first pattern that we're going to look into, and actually the first two, they fall in the same scope. They would be about queuing, and the first one would be wasting some time in unrecognized queues. So the idea behind this category and why it is one of the most common is that when you're designing a mobile app and you're trying to implement some feature or page, you actually can have multiple processes running in your app, and you'll be utilizing multiple threads to run those processes in parallel. So even if the process that you're designing, if the page opening or any other feature that you're implementing is designed efficiently, if the process is fine by itself and you're scheduling things to run on multiple threads, you're still inevitably going to experience some bottlenecks when you're scheduling something to execute on a parallel thread, like in this example here. But then instead of the function that you're scheduling to implement, to execute on a parallel thread, would only run after a certain delay. And that delay will not be due to the process that it is a part of, but due to some unrelated stuff going on and blocking the thread that it's trying to execute on. So it is most common to happen on the main thread because main thread is a natural bottleneck and there is a lot of stuff that can only be executed there. However, it also happens in other dedicated threads for any particular purpose, such as any local database updates, but there are many more examples. And with this, I'll pass stage to Brian to give his insights from engineering point of view and dive deeper into more particular examples of when it is common to happen.
Thanks, Anastasia. That's a great description you gave of unrecognized queues, and let's try to add a little bit of concreteness to it with some examples. A big problem or big reason that we have unrecognized queues is that a lot of times it's an implementation detail of a library or other dependency that we're using. For example, in this diagram, we're showing behavior of a very popular OK-HTTP library, which is not only used a lot, but it's also a dependency of lots of popular other popular networking libraries, and even in some video streaming applications like or libraries like Exoplayer. So in this example, we have something happening on the main thread, say a button push or other user interaction, and it wants to trigger a network request. Well, on OK-HTTP, the default dispatcher, this isn't really that widely known, but it has a limit of 5 concurrent network requests. So if you have 5 network requests going on when you try to launch your network request, it will have to wait for one of those 5 network requests to complete. So we're showing here in the diagram that thread number 2 completes its network request, and then finally our network request, which is a 6th network request, can be added in another thread to retrieve some data. And this isn't just an example that's specific to OK-HTTP. There are lots of other places where it can occur, such as in the room database, where you can only do one transaction at a time. And then there are also cases where we make sort of a coding, maybe we're not understanding exactly how the code works. We've seen this quite a bit where, say in an RX Java application, you might map or flat map or maybe you're just writing a Kotlin for each statement, and you don't realize that even though this is functional and it operates across a collection, it's going to do everything sequentially and not in parallel. So it's very difficult sometimes to imagine what's going on, and you really need a tool to help you understand what's happening there.
So the second pattern that we're going to address is actually very similar, and in some sense, it could be seen as a subcase of the previous one, and that is about main thread overwhelm. So this is something that a lot of engineers are aware of and tracking it, and it concerns the case when, well, there is just a lot of stuff going on in main thread, and then the reason why it would affect users' experience is that a lot of things, especially related to the UI, can only be executed in the main thread, which includes rendering and showing each of the frames that you see on the screen. And in particular, in the cases when user experience is supposed to be smooth and you have some continuous process showing on the screen, such as scroll, animation, some smooth transition, when you want to see those frames changing one another smoothly and evenly. In this case, what happens is that the space for the queue that you can afford is getting shorter. So as an example, the more advanced our phones become, the more advanced technologies we get, the higher refresh rate both phone companies and app developers, the higher frame rate you want to show. So now on the most modern Android phones, you can get frame rate as high as 120 Hertz, which gives you a space between two consequent frames as little as between 7 and 8 milliseconds. And that's really tiny amount of time. And in this time, what you have to fit in is rendering of the next frame and any other processes, any other events that you want to execute in the main thread, which could be, you know, setting up some libraries, doing some other stuff. And because you need to fit in everything in this tiny amount of time, it kind of shifts lens from the way how we looked at the queues in the previous part, and where you had this like big process final point, and you were concerned about large delays, about larger queues. So when it gets to the main thread, even tiniest delays, even like as little delays as 10 milliseconds would already affect user experience. And as you can see on the scroll example, it can cause a frame here and there to drop out, cause jittery experience, and it will be immediately noticed by the user, unlike in the other cases where 10 milliseconds delay is something neglectable. So with this, again, over to Brian for his engineering insights.
Thanks, Anastasia. That super point about the small amount of time. We usually look at 60 frames per second, which is about 16 milliseconds per frame. And like you're saying, 10 milliseconds is 10 milliseconds that doesn't need to be there is chewing up most of the time that you have on a frame. One of the interesting points about frame rates is that you can't really just rely on Android to tell you when you're dropping frames. Android only messages you in the logcat when you're dropping 30 frames or more, which is around half a second, 480 milliseconds of delay, and that would be very noticeable in just about any app, in any circumstance. So it's really important to pay attention to this yourself. And I thought there was a great example of a very popular Android library called Lottie. And there was a post by Gabriel Peel recently that was associated with an update, the most recent update to the library. Lottie is an animation library, and there are two functions that it does. One is it will draw the animation on the screen, and then it will compute an update for the next frame. And the way that this was working prior to the most recent update is that the update to the computations that did the update were actually happening on the main thread prior to drawing. That's demonstrated in depicted in this diagram on the right. And what happened was they moved the update step onto a worker thread. And so you can see that down below in the slice. Now we're drawing the frame based on the last computations, and then immediately we can start doing the update while freeing up the main thread. And you can see that now there's so much extra time on the main thread that other visual elements in the UI can use to draw themselves or do whatever, inflate, do the layouts, all of those things that have to happen only on the main thread. So furthermore, you can see that the update was actually quite a bit larger than the draw. So it's a really inefficient way to do it. And even though it was more complicated and involved, going into Java synchronization and locks and that sort of stuff, it's a huge improvement for an animation library that's drawing very frequently on the screen. So.
And with this, I'd like to turn to the second part of our presentation, because as I mentioned, the patterns that we're going to talk about today, they're kind of split into two groups, and they're also like highly intersecting like the previous two. So we just discussed the case when the process that we're looking into is on itself designed well, like we're not looking into optimizing that process, but we are looking into how it interferes with the rest of things going on in the phone. And then now we're shifting the lens to the process itself and to how we can actually optimize execution of like whatever flow we're looking into. And here, kind of all next three categories, they would be concerning pretty much one pattern, and that is, again, as discussed previously, you have this amazing opportunity to schedule things to parallel threads, to execute stuff in the background, which is amazing. It allows you to shorten valuable users' wait time. So now what we see often happening is that a very simple thing, just something that could be running in parallel with the rest of the application, with the rest of the flow, is dispatched to a parallel thread later than it could be. And kind of like the general rule of thumb here is to dispatch things to parallel threads as early as possible to shorten users' wait time, to parallelize as many things as you can. However, even though it sounds simple in theory, it is almost impossible to achieve in reality, because we don't ask ourselves this question, but like when writing every single line of code, oh, like, is it already time to dispatch something? Can I do this thing in parallel? You don't think about this constantly. So that is the reason why we kind of identified the three most common situations in which this dispatching happens too late. And some of them are intersecting, but basically these are three cases in which, like, when writing this code, it's worth thinking already, like recognizing this point and thinking whether this is like the point when something should be already sent to a parallel thread. And also, if you're trying to optimize the already existing code, please take a look into these points. Those would be great kind of starting points to look for inefficiencies, to look for performance opportunities for optimization. And the first one is my personal favorite, is the unnecessary UI dependencies. And that is something that surprised me the most at some point. That concerns the case when a certain part of the app that runs in the parallel thread that's not visible to the user, very often that's loading of some content that's happening, like loading it from the server, that's happening completely in parallel, would be dependent on a certain view update. That often can be an animation, or like on this example, imagine you have an app and you're sending two network requests to fetch different kinds of data. Those requests can be interdependent. The second one needs data from the first one to start. So it's okay to send them in sequence, that's fine. But what we see often happening is that the first network request arrives, the data from it is parsed, it updates the UI, you probably rebuild the view model, you do some other stuff here, it takes time. Only then it will result in the UI update running in the main thread. And from there UI update, you would schedule the second network request, which itself will show some data on the screen. Now, what we see is that, and what we recommend in these situations every time, is not to wait for the second network request for the UI update, to schedule it as early as possible once the data from the first request is parsed. And this way you will be able to show data from this request, maybe just a few frames earlier, but maybe significantly earlier. It can actually save you sometimes seconds of wait time. And one last thing that I wanted to mention here is that the animation, if the UI update that you're waiting for is the animation of in the beginning of page loading, that happens very often, and it can be considered as a product decision to do some smooth transition, to do revealing of something. So very often these cases fall under the radar, and that is because one would be considered a product decision and just like design decision, but the second, the loading time would be only counted like for the network request, for the actual loading time. And if these time segments do not intersect, you're actually running into the situation when you can count them separately and not realize that they both add up to the user's wait time and create this delay. And with this, for more details and his wonderful insights, I pass the floor to Brian.
Thanks, Anastasia. That's a great description of the problem. And we also have an illustration with some real apps. In the bottom left corner of this slide, we have two apps for viewing stocks. And what you can see is that we have taps on each screen. They both animate to the next screen, but the app on the left is much slower at displaying the data that's retrieved, while the app on the right is, the data is appearing much more quickly. And that is because the data in the second instance is being retrieved while we're transitioning to this new piece of UI and doing this animation. So one of the reasons that this happens is, like, a lot of times when you're learning how to do development on a platform, iOS or Android, you're taught a certain way to do it, and that sort of sticks with you. It proliferates through a lot of examples. And so you'll have situations like this code that I have on the right, where you have, say, a list of stocks, and when you tap on a stock, you make a transition to a new activity or fragment. And then once the fragment has animated onto the screen and inflated all of its views and done all the work that it needs to do, then you start to load the data. Well, it's very simple. It's not totally simple. You may have to do some architectural changes and add some listeners and that sort of thing. But you can actually move the couple of lines of code in this example at the very bottom of the screen that have a client new call. We can move that up into the button click listener or click listener above, and just start the network request as soon as the tap occurs. And that's going to make, the animation becomes more delightful, because you get to watch the animation, and as soon as the animation is over, instead of waiting, your data is appearing. So.
And I promise to go faster with the next categories. So here, the first pattern is highly intersecting with the previous one. Even the examples that we showed kind of were on the intersection of these two. And those are about network requests being scheduled too late. So the reason for identifying it as a separate pattern is that network requests usually take, in most of the apps, when you're fetching something from the server, network requests will take the most of the user's wait time. So pretty much anything that you can do around rescheduling them and around running them in parallel would save you that time. And often, like, that is the most significant optimization that you can do on your phone. So often it happens that when you're dispatching a network request to actually run to the server, you're making a choice of when to schedule it. And the idea is that as early as you can do it, you should be doing it. But what happens often is that you're waiting for either a UI update, as in the previous example, but also there could be other stuff. Many examples come around the app start, and Brian will talk about it in a bit. So anytime when you are scheduling a significant network request that your user will be waiting for, just give it a second thought and ask yourself whether it could actually, whether you had enough data, whether you had everything set up to start it earlier, like in the example here. Brian, over to you.
Thank you. So one of the interesting things about looking at traces around app starts, which obviously very important to everyone, first thing the user sees, is that we start seeing these really long app starts where all kinds of work is being done. What we discovered is that it's very common. We're using a lot of libraries and apps these days. It could be, analytics libraries or some kind of authentication or maybe crash reporting, all these different things that tell you, hey, do this initialization in your app on create. And that's fine. But sometimes you can wait and do these things later. You want to offload what's happening at app startup. You can get to a screen more quickly. Maybe if you have something like a network request, you can kick that off in the service or something like that before you start loading all of these other libraries that you're going to be using later. And then a final and very interesting aspect is we've noticed that dependency injection can be impactful here, because dependency injection will inflate an object graph, which is notoriously time consuming to build a bunch of objects. And if you don't have proper scoping on your dependency injection, you might be loading things at an application start that could be done later in an activity, or maybe not even done at all if you never reach the part of a user flow that needs that particular set of objects.
Let's jump to the next pattern, and that is also related to network requests. And the reason for that is, again, as I said, because network requests are eating up most of the user's wait time in most of the processes in your app, in most of the page loading scenarios, you need to fetch data from the server. So the case that we see pretty often, I would say less often than late scheduling, but still very often, is when the network requests that could be running in parallel are executed sequentially. And there can be multiple reasons for them. Sometimes it goes unrecognized that requests are in fact independent. So kind of the question to ask yourself here would be, if you can, if you have a sequence of network requests in your loading pattern, to ask yourself whether whether the second one or the third one needs the data from the previous one to run, or if you have enough to schedule them in parallel, or if you can separate them in such a way that they can be scheduled in parallel. And the reason why we always recommend doing it, and why we find this so significant, is that, well, often, as Brian mentioned, those patterns go unrecognized because they are thought to be issues on the backend side, and they require a lot of resources to be fixed. But it turns out that a lot of network optimization can actually be done on front-end side. And if on the backend you will be fighting for just a few percent, maybe 10% of optimization would be already great. Here, if you put two requests that were running in sequence in parallel, you can easily save something like between 30 to 50% of the wait time. Realistically, what will happen, you'll take the shortest of those network requests and you will cut its length completely by 100%. So this is very cheap improvement in this sense, but it gives you extreme gain in sense of time that is saved. And with this, Brian, over to you for your insights.
Yeah, thank you, Anastasia. One of the main pushbacks we get on this is an argument about bandwidth. And it's true that this is a latency versus bandwidth trade-off. There's some overhead associated with doing a bunch of network requests, and making too many can impact the amount of time it takes previous network requests to complete. I would just say this is a place you want to do testing. And what we found is that unless you're doing something that's very bandwidth heavy, like streaming video or doing downloads, you can almost always see significant improvement by parallelizing network requests whenever they're available to you. Usually the problem here isn't recognizing so much as making sure that you have all the information available to parallelize.
Please don't hesitate to reach out to me, Anastasia, or Brian, find Lincoln or our team. Contact our team directly at productscience.ai for any questions regarding product science overall, the product specifically. Thanks again for joining us today.